Michael for the nice introduction. It's a bit complicated, but so okay. Today I will speak about work that I've done mostly with a PhD student of mine. So he's called Louis Lecomte. So he's working at Lagrange Center of in Mathematics and Computer Science. So it's a kind of lab which is founded by Huawei in France. Mathieu Jonker. So Mathieu Jonker is a very old friend of mine, so he's more somewhere in, so you don't know him, of course, but he's not young. He's doing some queuing theory, and you will understand why there are some queuing problems there, and myself. Okay. And thanks, Pranit, for invitation. And I'm very long in general, so I never speak quarter of an hour. You know, it's like I am an old leftist from France, so I speak and speak and speak. You know, it's like. Okay, so what is the problem? I will start with problem formulations, and I will try to speak a little bit about related works, or not much. Then I will do some numerical analysis, and then I will conclude. Nothing very fancy. So the problems that we will address, I think most of us today. So it's good to have the first slide on that. So it's about federated learning. So I look at the most simplest case of federated learning. I do a lot, especially in EIU. I do a lot of work on federated reinforcement learning, but I will not speak about federated reinforcement learning, despite I think it's a very, very nice direction to go. So in the classical federated learning, what you do, you are looking at the classical supervised machine learning paradigm, and so what you are looking at, you are trying to optimize the parameter x, okay? And this parameter x is the minimization of a function which is defined as a sum over n clients or devices. Each of these sum is a kind of a local loss function, so which is defined as follows, nothing very fancy then. And you are trying to minimize the sum of this function, which is empirical loss. And there are many, many problems which can be formulated like this. So I'm looking at what I call lower non-convex optimization. There are, of course, much finer results which can be obtained when the function f is convex, but I'm interested more in non-convex optimization. I will not derive super precise bond. I will left Emmerich to introduce you to a more when you are looking at the convex function. Of course, the results can be made much more precise. Okay, so what is asynchronous? So the classical technique to work with this type of problem is to work with as a synchronous distributed gradient descent problem. So what you do, so you have data sets, D1, Dn, so you have n clients, and you have a central server there. So the central server has a current model, which is denoted by xt. Then this model is dispatched to all the clients, okay, so which receives these parameters. They feed this parameter into their models, which is a nice multi-layer perceptron here, or I don't know, so perhaps it's a multi-layer perceptron. And so they have their local data, and they start to iterate. They compute a gradient, or it can be also, of course, a mini-batch gradient. If you are doing SGD, would be more likely to be a mini-batch gradient. And then what you do, then you just back up this gradient to the central server, and then the central server updates the parameter, so define updated models with some step size which is denoted gamma there, and it will be denoted eta later on. Okay, why? Because I've stolen these slides from one of my interns, Rustem Islamov. So we don't use exactly the same notation. So Rustem was more an intern of Emmerich. So he was a PhD track with Emmerich. He has been stolen by Switzerland, you know, recently. Okay, so now what is that synchronous model? So which means that all the communication are synchronized, and so in general setup, the problem is that you have to wait for the server waits for the slowest worker, so which make problem, especially if you are in kind of cross device settings, or where you have a lot of users, and perhaps you will have some users are very, very slow to answer. So then you have many, many ways to define what is an asynchronous distributed gradient descent. There are many works. I will just describe some of this work later on in the literature survey, but there are many works. I will define the problem, and I will just present the algorithm I was looking at. And it works as follows. So now I start from time 0. So at time 0, I have also a central server, which is, I don't have a pointer there. Sure, but I should. So at time 0, you have a model, which has x0. So this model parameter is sent to all users. Okay, so these parameters are fed to the users, like this neural nets, and then they start to compute. But the thing is that you start to compute, but they don't compute at the same speed. Okay. They don't compute at the same speed, so they all start the computation of the gradient or stochastic gradient. And what happened is that, the first which has completed his work is client 1. Client 1 was the fastest, so he finishes to work faster, so he can send back his gradient estimate to the central server. Okay? And what the central server do is that is updating the parameter, okay, but without waiting, if you wish, that the other answers. In such case, you are not stalled you are not in the process of waiting for the other users to answer. So you update, and you have a new parameter x1, okay, which is updated according to this one central server. Then, and all the differences of the algorithm from here. So the central server decide to send this model to another user, okay? So here he repick user 1, okay, but it's not, so if you do that deterministically, it's not a good idea, so it will be bad. It's easy to understand. If you have very, very fast user, he will finish very quickly, then and will answer, so he will answer more soon. So you don't have to do that. You will have, so typically what you have to do is that you have to resend, in fact, with certain probability, I will discuss that later, you resend the job to other users, and of course, if a user is already active, he has to stack the job because he's in the process of computing one gradient, and he has to stack the job, and he will process the job later on. Okay. So then the second user comes. Okay. So the second user was still working with parameter x0, send back his update, but the update now is x1. Nevertheless, you get an update there, so you make it x2, okay? You update with a gradient update, and you update with a delayed gradient, because of course the gradient which is here is not, you update according to a gradient which is delayed, because you already have updated the gradient with the first user, okay? So there is some kind of delay which occurs in the asynchronicity, and which makes the analysis of this algorithm a little bit more tricky than the classical analysis of synchronous algorithm. Okay, so that's the delayed gradient, and which makes all this difference. And the delay, as I said, may come from the fact that some of the job has been stacked. So because I did not show a queue there, but there is a queue which is building, because when you will resend, when the central server will decide to resend the computation, perhaps one of the users was already computing a gradient, so he has to stack. So there is a queue which is building up, a queue of gradient to be computed. Okay, so that's the overall algorithm I was willing to analyze. And so the main message there is that the communication is asynchronous, and the server applied delayed gradient. So you solve one part of the problem, but you have to cope with asynchronicity. So this is a general asynchronous algorithm I will look at. So of course you can make it more general. So and we have somehow some more general analysis, but to keep the thing simple, I define it like this. So you at a given iteration. So what you will do? So you ask at a given iteration. So you look at what is k here. It's not a time. This is why I don't use. Because when you look at a synchronous algorithm, you have to define what are you looking at. So are you looking at time, okay, or are you looking at iteration of server steps, okay? So I'm looking today. I can look at time. Also, I have some results linked with time, but here I look at time measured in terms of number of iteration of central server, okay, which is something different. So k is a iterate of the central server. Okay, and what I do here, so at iteration k, there is one of the client or worker which is finishing his job, This job is called GK, so it's a random variable, of course. It's a server which is finishing its job, okay? G of GK is stochastic gradient estimate, okay? And of course, it corresponds to the parameter which is used by user GK is IK, because it's a kind of parameter which is taken from the past, okay? IK is less than K because we are not synchronous. And K minus IK, which is denoted here, is in fact it's the delay by which we are applying the gradient. Okay? And what we do next is that we update the current model. We update the current model according to this formula, so xk plus 1, so it's g of gk xik. And what I'm taking into account is the probability, so it will be important in my talk. So there is a probability. The only thing that we do is that we reallocate the job for the user with a certain probability. So it's a very simple policy, but it's compared to classical asynchronous gradient algorithm, we use a non-uniform policy. So we reallocate the job to different users with a certain probability, okay, which are not uniform, and I'm taking that into account by dividing the update step by this probability P of the user GK. Okay? And then what the server does, it just assigns the new work KK plus 1 to compute the new asymptotic, the new stochastic gradient, which will be GKK plus 1 of xk plus 1, that will be used to update. So I could generalize that a little bit. I could have had a delay there if I would like to analyze a strategy which are good strategy like fed buff, for example, where the server did not necessarily update immediately the parameter. I have 10 minutes left. No,
10 minutes done.
Done. I did not start. Okay. Okay. So you could imagine to have something a little bit more complicated there by adding some delay, because you can buffer. You can make a buffer of updates. Okay. So you can buffer the update and decide to update the parameter after. For example, if you have received, say, B updates, then you update. Okay. Sometimes it's better to do that, but I did not do this analysis there. Okay. So of course the clients IK which are returning to the central servers comes in natural order. Okay. They are not controlled by the server. It's like they just return to the server because they are finished to do their job. Okay. But the server decide how to set, in fact, the next users that will process the next gradient. So there is a strategy, and this is a very simple strategy. So I think in the future we are imagining the way what we will do is that we will look at the status of the queues. Okay, so I think we will have a routing strategy. You can have smarter routing strategy. Here it's a random pooling, so we pool randomly but with non-uniform pattern. Okay, but of course we don't take into account that some user, for example, might have a lot of gradient to compute. And we did not take that into account yet. Okay, so related work. So I will go fast, especially because there are a lot of experts in the rooms, which are much more experts than me. I see Gorbunov, I see Sam Horvath, so I will not be. So look at this. A lot of work which has been done since French guy, Baudet, which was the first to analyze this type of stuff. I was 15 years old, long time ago. I don't know Baudet, but Bert Sekas did the first analysis, asymptotic analysis of synchronous gradient. There are a lot of work which has been done by you, Pranit, with fixed delayed, Arjevani. So there are a lot of work done by the EPFL team with Koloskova, Mishenko, to me, in fact, so I started by looking at this work at Koloskova, and I think there is something that can be improved. I will explain. So because they all assume some kind of maximal delay, okay? And maximal delay gives you bounds which are extremely pessimistic, okay? There is a kind of maximal delay because you have, if you look at the dynamic of the system, at the beginning of at the initialization, you start C jobs, okay? And the number of jobs in the system is always C, so you have always C clients which are working, okay? And and the maximal delay can be computed like that. Okay. So our theoretical analysis is done as follows. So we use very, very classical set of assumptions. Lipschitz functions. So we use unbiased estimator of the gradients with bounded variance. So we take bounded variance there, so we can use more better assumptions, of course. We have also the classical heterogeneity assumption. I think it's a G square because it's an old version of the slide, so G square later on in my slide. So it measures the heterogeneity of the gradient. And we have also some locality. And then the quantity which is important there is MIKT, okay, T being the last time index. So MIKT, in fact, it looks a bit strange, but in fact, in words, it means what? It means that that is a number of CS steps, okay, of central server steps that need to be elapsed when you send the gradient to client I, okay, and this will be the time to wait until the gradient will be processed, okay. So XIK, there are the length of the queue, so the number of tasks on the client I which has not been processed, and GL are the index of the clients which are currently released, okay? And that's a quantity which is really of interest, and the quantity which is very important in all the analysis is this MKT. So MKT is the sum of the expectation of this quantity. So it is related, so the quantity which is very important in our bound is, in fact, what is the average time, what is the average number of time steps that will be elapsed when I send the gradient to client I until, in fact, the gradient will be processed, okay? And that, the analysis is not different from the analysis by Koloskova or many, many other authors in the sense that we have a kind of virtual iterate, so there is nothing very, very fancy there, okay? I'm finished already. And there is nothing very fancy there, but the thing which is important is really that so we express all these bounds in terms of this kind of expectation. Okay, so our bounds, in fact, are much, much better than the others. No surprise, okay? We have that's our efficiency factor, so it's more than 100 somehow, so depends in the configuration. And this is because we take a kind of very simple scenario with 100 modes. We have 10 fast clients, 90% of, and then what we call μF, in fact, is different speed between we have two groups of clients, 10 fast, 90% slow, okay, 10% fast, and μF is, in fact, it's a ratio of speed between the fast and the slow, okay? And of course, the analysis of Koloskova is really bad because, or even FUDBUF, because they are penalized by the fact the way that you have this tau max, which is very large in their case, and which is doesn't need to be large. Okay, so, and now how it is related to, and I finished Pranit, I promised, how it is related to Jackson networks. In fact, it's a closed, in terms of queuing system, it's a closed Jackson network. So which means that you have a central server, okay, and you have queues, okay? The number of works in this net is always C, so you only have C. So you send C process, and you will always have C gradients which are computing right now. So which means that the C delayed gradients. So maybe they are in queues, okay, or they are currently processed, but you have only C gradient to process. So you have, it means that you have a C jobs in the network, and the number of jobs in the network, which is called sometimes the concurrency, is fixed during all iterations. And what you can prove is that there are a lot of work. I will not have time to explain, but there is a lot of work on these closed Jackson networks. You have, for example, you can define what is the dynamics of the queuing system. So how many at time t, and now t is really time. It's not like iteration time. Okay, it's t is really time. At time t, what is the number of clients in each of the adjoint queues? Okay, so that you can define it. It's a Markov process, assuming that you have, in this case, I assume that I have exponential, it's Poisson process, which means I assume that each work takes a kind of independent exponential time, because it's much easier. I could have general processing time, even random processing time, even deterministic processing time is doable, but it's much more complicated because then you have to define what is called the edge process, which is more complicated, but it's very, very simple in the scenario where you assume that each job takes a kind of exponential time to be processed. So it's, and then you processing time. So μg is the intensity of this of the jump process for each client, and pi are this the probability of setting choosing the client I. Okay, and you see that the distribution of the Q depends on theta I, which is the ratio of pi over mu I. You can also obtain a kind of expression for asymptotic expression, at least for the delay, according to what is called the Palm probability there. So EC minus 1 is the Palm probability. So you have an explicit expression for this average delay. And so it's a bit difficult to explain what is a Palm probability here, but it's a classical method in queuing theory, at least. And of course, what we have done also is that we can have a very explicit expression of this MIKT in what is called the heavy traffic regime. So heavy traffic regime means that most of the time all the queues are full. Okay, so which means that all the time, otherwise it's very, very complicated. So it's because there is something to understand just if you are a bit in queuing system, is that if all the queues are full, because we have Poisson. You have Poisson variable. The delay is very easy to compute because it's like it's always because of the memoryless. The exponential distribution are memoryless. In fact, it's always the time at which you will observe a point is really like distributed according to. It's always distributed according to an exponential. It's an exponential time with the intensity, which is the sum of intensity of the Poisson process. So that's so a lot of things can be done. So we can interpret most of these patterns. This is done in our work. We did not put that on archive, so it's very fresh. It has been submitted to ISTAT, but we did not release it on ISTAT. But I can share if you wish the current version. It's not. Yes. Give me 1 week to really clean all these things. But we can using this. Heavy traffic asymptotic, we can retrieve, in fact, at least in some cases, we can retrieve the part. And the thing which is very important is that you gain a lot. You see that, I think, there. I'm not sure I've included this, because I did that. I was taken by time yesterday night. Michael was calling me to restaurant, and so I did not have time to finish. But you will see. He said, Eric, you should come. So we have a wonderful meal. So this is why I put the slides. I was trying to finish. It's your fault. And so you can show there that, in fact, it's the use of non-uniform pattern is very important. The fact that you use PI, which has not uniform, if you want to have a large gain, in fact, you need to use non-uniform probability of a signing job. Okay. That's very important. Okay, so it's not, and the way it should work, it's a bit intuitive in the sense that it's a bit counterintuitive when you think, is that you should assign job more frequently to slow users, contrary to what people believe. And I will explain to you. It will be a quiz. Why? In fact, intuitively, you say, okay, so you should not pull more often fast users. You should pull more often slow users. Okay, thanks a lot. So if you are interested, I can share the current version. It's not perfect, but it's there. And yes, ready for question.
Yeah, while Mike's setting up, maybe there's a quick question for Eric. If there isn't, I can ask one. What do you think? How do you think lower bounds would work in this kind of a setup? So, what would be like the tightest lower bound we could hope for?
I think it's difficult. So there are many things which remain to be done. So we don't use control variate there. So it's like very, very brutal stuff. So I think, I don't know. But I think we are very far from... so we just noticed that, in fact, the message is that the way people... so we did not really change the analysis. It's more like the way people upper bound, in fact, what is called, I would say, the variance of the gradient. And because to take into account the fact that the gradients are not updated at a regular scale is very, very brutal and very pessimistic, okay? So which means that you can do much better. And the second message is that assigning non-uniformly users is a good idea, and it's really linked with, you can optimize somehow the way when you know the speed of each user, and it's a bit surprising. The way you should do it is a bit surprising. Yeah, it's not completely intuitive.
Thanks, Eric.
Thanks. Back, it's your turn. So